Language models can write a coherent sonnet on command, but ask them to multiply two four-digit numbers or look up today's date, and they fail. Adding more parameters to the model only partially addresses these algorithmic gaps. A larger model simply becomes a more confident guesser. The first obvious fix is to wire a tool directly to a specific task, like a dedicated calculator for a math dataset. This solves the immediate problem but destroys the model's general applicability. The second approach relies on humans manually annotating thousands of examples, labeling exactly where the model should use a tool. This is expensive, and it assumes human annotators actually know where the model's internal representations require external data. In 2023, Meta AI published the Toolformer paper, offering a third path. Instead of relying on humans, the model acts as its own teacher. It uses its own localized prediction error as the ground truth signal to figure out when a tool is useful. The researchers took a 6.7 billion parameter GPT-J model and had it autonomously annotate a standard pre-training corpus to master 5 different APIs, entirely self-supervised. By building a self-supervised data construction pipeline, Toolformer bypasses the human annotation bottleneck. It bridges the capability gap while retaining the model's general language skills. The base architecture is GPT-J. The target is 5 distinct APIs: an Atlas QA model, a BM25 Wikipedia search, a calculator, a calendar, and an NLLB translation model. The critical constraint here is that all 5 APIs share a strict text-in, text-out interface. The model generates a text string to call the tool, and the tool returns a text string as the answer. To format these calls, the model uses open and close API tags. Crucially, these are existing byte-pair encoding sequences. Because the model already knows how to produce these brackets, there is no need to modify the vocabulary or perform embedding surgery. This pipeline maps phase A: sample, execute, filter, merge. In sample, the model uses a few-shot prompt to aggressively overpropose candidate API calls where token probability exceeds a threshold. Next, in execute, each candidate runs against its API, returning a text result. Because the first 2 stages intentionally flood the pipeline with noisy, often useless candidate data, the system requires a ruthless mathematical pruning mechanism to isolate the actual signal. This brings us to the central engineering challenge. Given a candidate API call and its returned text, how do we mathematically prove to the model that the result was useful for next token prediction? The dropping vertical bar represents cross-entropy loss with the API result provided. It must drop below the double floor baselines, making no call or calling but hiding the result. Beating both baselines proves the data is unique, preventing useless no-op calls. To ensure relevance, a locality weighting is applied to the loss. This weight zeroes out after 5 tokens, meaning the reduction in perplexity must occur strictly locally to the call itself. During the data generation phase, the API result is fed to the model as a prefix, rather than spliced mid-sequence. Because the base model hasn't learned to read in-sequence calls, inserting them midstream would cause artificial perplexity spikes and contaminate the measurement. Stage 3's contrastive filter acts as an automated, math-driven teacher. It prunes the noisy dataset, keeping exactly the calls that quantifiably improve immediate token prediction. In Stage 4, the surviving high-utility API calls are interleaved back into the original corpus to create an augmented dataset. GPT-J is then fine-tuned on this augmented dataset using standard language modeling objectives. With the model trained, Phase B, Inference, uses greedy decoding but modifies it with a specific top K boost. If the API token appears anywhere within the top 10 most likely tokens, the system forces it to fire. It lowers the bar from requiring the absolute argmax, ensuring the tools are actually utilized. There is also a strict cap of 1 API call per input. This is a hard-coded guardrail implemented to prevent the model from entering infinite API generation loops. This diagram illustrates the physical inference loop. Text generation pauses the moment the model emits the arrow token. The system calls the external API, splices the returned text result back into the prompt, and resumes autoregressive generation. Through this pipeline, the model learns to autonomously initiate, pause for, and ingest external API data as a native component of its standard generation process. Comparing benchmark scores on the Llama and math datasets, The Toolformer 6.7 billion parameter bar significantly eclipses OPT66B and GPT-3 175B. Deciding zero-shot to use QA and calculator tools 98% of the time, it doubles baseline performances and outperforms GPT-3, despite being 30 times smaller. To understand when this capability develops, the authors trained smaller GPT-2 scale variants, ranging from 124 million to 1.6 billion parameters. The ability to self-teach tool use does not scale linearly. It is an emergent capability that sharply materializes around the 775 million parameter threshold. The paper advertises no cost to general language modeling ability, but there is a caveat. This preservation of perplexity is technically only proven when tool calls are explicitly disabled at inference. Self-supervised API integration provides an incredibly efficient alternative to massive parameter scaling for workflows requiring specific factual precision. The elegant simplicity of this self-supervised design creates three strict structural ceilings. The first limitation is an absence of chaining. Because candidate calls are sampled and scored completely independently, the final training data contains 0 examples of consecutive calls. As a direct consequence of independent sampling, the model inherently cannot learn to compose tools or iteratively refine search queries. The second limitation is that loss reduction does not equal correctness. The contrastive filter mathematically checks only for a drop in cross-entropy loss, not for factual truth. If an API returns a confidently wrong but syntactically predictable answer, it will easily clear the threshold and inject hallucinated validations into the training data. The third limitation is severe sample inefficiency. The data generation phase demands massive compute overhead, requiring a scan of over 1 million documents just to isolate a few thousand useful calculator calls. Historically, Toolformer served as a pivotal proof of concept. It paved the way for modern function calling models, trading self-supervised elegance for supervised multi-turn reliability. Despite limits, Toolformer proved an LLM's own prediction error is a precise enough signal to autonomously teach it to interact with the outside world.